Hello again and welcome to the Wire-EDM YouTube channel. In my previous videos you might have been annoyed by the bad audio quality, and so was I. So I've switched to a decent microphone, so that problem has been solved as of now. Okay, I've been really busy with the arrival of my industrial die-sinking EDM machine, the Charmille Ileroda 110, and it's quite a thing. It's going to take me a significant amount of time to get this thing back up and running and to retrofit it. So for this, I'm going to dedicate a YouTube series on this channel. So subscribe to Wire-EDM and then you can monitor the progress in the future. For today, I'm going to continue with the MK2 redesign of my Wire-EDM machine. So in the last video I've shown that the Fusion 360 model was finished, and now the mechanics have been finished, which was quite a bit of work, and it's time to start testing to see if it does what I intended it to do. So let's have a look. Here's an overview. In the top left corner there is the pinch mechanism and the clear path motor that drives it. So this determines the tension in the wire. On the right next to it is the capstan mechanism and another clear path motor that determines the wire speed. Then the wire goes through the top wire guide, after that to the bottom wire guide. You can see the wire contact there as well. And then it goes back up to the pinch wire mechanism, which ejects it into a tube, into a container that captures the spent wire. As you've probably seen in one of my previous videos, the previous design iteration had some problems with the wire slipping. Also, the radial load on the motor was too high, and there were fluctuations in the tension of the wire. So I'm really eager to start testing these properties now to see if this design iteration fixes all of those. But first, let's have a look at how to rethread the wire in this pinch mechanism. Okay, so the wire now has one open end and has no tension on it. So let's put it back in the pinch mechanism and see how that works. So you take the wire and guide it around a roller, the lower rollers. Up to the top roller, the clamp has already been opened. Then you simply push the wire into the tube. And you close the clamp. Give the wheel a twist. And that's it. So the first thing that I wanted to test was to see whether or not the wire pinch mechanism has enough grip on the wire. So I took this section of wire and soldered a copper eye to it, piece of copper, so that I can interface it to my force gauge. And then I can do a pull test. So I set the force gauge to measure the peak, and then I start pulling until the wire breaks and see where it breaks and what the force is. So let's have a look. Here we go. Snap. Okay, so the force is 32.9 newtons. However, the wire broke at the interface to the force gauge, so this measurement is invalid. So, second attempt, I just took the EDM wire and spooled it around the hook a lot of times and taped it to fix it. So the capstan effect should now hold it in place. So here I'm putting the wire into the mechanism, securing it, and let's do the test again. Reset, and here we go. This time the force is 40 newtons, 40.4, and the wire broke at the pinch point. So 40 newtons is Very good. I was aiming for about 30, which is already really high. In practice, it will be somewhere between 20 and 30 newtons. And yeah, I'm really happy with this. Okay, instead of me pulling the wire, let's have the ClearPath motor do it. So now there's no tension, and I use a serial terminal to turn the tension on. That seems to work. Just a bit more. Yeah. Bit more. Nice. You could make a musical instrument with a single wire. Okay, I'm happy with this. Okay, enough with static testing. Let's get this wire running and see how it behaves. So first let's tension the wire. Now it's tensioned. And now let's start the wire up at a low speed and see what happens. Oh, this is not looking good. The wire fluctuations have returned. I was not expecting that. Let's test at a different speed and see what happens. Here's the wire running at a higher speed. As you can see, the fluctuations are still there. The frequency of the fluctuations has just increased. So this is not good news, because I was hoping that the move to the ClearPath motor and its torque control mode would resolve these fluctuations, but apparently it doesn't. It's a bit hard to see what these fluctuations are about while only looking at a rotating gear, so let me show you in another way. Here I'm tensioning the wire now, and now I'm sending a command to run the wire. And now I'm pressing against the wire, and I'm trying to keep my finger still. I'm not moving my finger back and forwards. The variation or the fluctuations in the wire tension is causing this. Here you can see that this is clearly undesirable. We need to have a constant tension force. So, unfortunately, the wire tension problem has returned. Now, where do these fluctuations come from? Well, they can have a lot of different sources. First of all, a disturbing force that I did not consider first is that the wire rollers deform the wire. So the wire that comes in is 0.25 millimeters in diameter, and the wire that comes out is 0.18 millimeters in diameter. So the rollers squish the wire, which means that force is needed in order to do that, and that energy is subtracted from the torque that you put into the mechanism. So the torque you put on the axis is not directly translated into tension of the wire. Next to that, there are also disturbing forces. Bearings are not exactly perfect. Teeth of the gears are not exactly perfect. There might be a slight runout in gears or in the mechanism. And the rollers themselves, they're not exactly perfect as well. So if you take into account all these imperfections, then a disturbing force is going to be the result. That is inevitable. So if you determine the tension in the wire by only determining the torque applied by the motor, you are going to have these fluctuations. So indirect control, which is controlling the torque of the motor, instead of direct control, which is measuring the tension in the wire and then controlling the power of the motor, indirect control is always going to be inferior. So I'm afraid I'm going to have to switch back to the plan I had with direct control, which I did for the first time in episode number 11 of this series. You might recall that I made this contraption here, which is a sensor that I made myself that has a strain gauge, and this sensor can measure the tension in the wire. And then with a closed loop control, you can control the torque to the motor. And this worked really, really well. Actually, I was amazed at how well this worked, because I was using really cheap motors and the fluctuations were really bad. But after applying this mechanism and control method, the fluctuations were completely gone, like completely. So this worked really well. However, this was kind of a bodge job, just to show a proof of concept. This is not something that I would like to put in a design for others to make or share. So I need to come up with a different solution. Maybe I can buy an off-the-shelf tension sensor, or maybe I can redesign this thing such that it is easy to make by others. Lots of work up ahead. Unfortunately, because I was hoping that this would be the solution. Because apart from the arc generator, the other things in the machine, such as the water handling system, the water tank, the positioning mechanics, things like that, that's all peanuts compared to the wire handling. The wire handling and arc generator are the two most difficult things. So if you have an arc generator, which you can buy from BacksEDM.com, and if you have a mechanism that can handle the wire correctly, then that's 80 to 90% of the complexity of the machine. The rest is super straightforward and easy. Okay, that's it for this episode, part number 14 of this MK2 build series. Hope you enjoyed it. Subscribe to the channel and see you next time.